Hey there, it's Shannon Gracey back again. Today we'll be covering section 1.4 from the Larson and Edwards Calculus text. 1.4 goes over continuity and one-sided limits. Go ahead and read the goals up top to see what you should be able to accomplish after you do your homework. And let's go ahead and warm it up. Pause the movie, do the warm-up, and see how you do. I know you can do it. Go for it. Okay, let's see how you did. Remember, when graphing, we want to make sure we're looking at a simplified rational expression. So let's go ahead and factor this guy and see what happens. So f of x can be rewritten as x plus 2 times x minus 2 divided by x plus 2, which is equivalent to just this line with the added condition that x cannot be equal to, good, -2, because that would zero out the denominator. Perfect. So what's going to happen with this graph? Are we going to have a vertical asymptote at x equal -2, or will we have a hole in the graph? Awesome, we will have a hole in the graph. So let's go ahead and make the sketch of this much simpler looking deal here. Make our scale from plus or minus 10, and then this will be x, and this will be f at x. And so we've got this in slope-intercept form. We have a slope of 1 and a y-intercept at 0, -2. And so we have 0, -2 here. And then using our slope, we can get some more ordered pairs. So if I go up 2 over 2, that's the same as a slope of 1, up 2 over 2. So this is going to give me this side of the graph. Now, what do I have to be careful of? Very good. When x is -2, we have to exclude that value, don't we? So at x equal to -2, we would have had an output at -4, but we have to make that an open circle to remain true to our domain restriction. Okay? How'd you do? Awesome, I knew you could do it. So what was f at -2? Undefined. It's not part of the domain. And what about the limit? So let's look graphically. The limit of the limit as x approaches -2 of our function is going to be what? Good, -4, because that's the y value. And from the right side, do you see we also get a y value of -4 that we're approaching? So therefore, we can conclude that we get a limit of -4 as we approach -2 from both the left and the right. Okay, how we do? Perfect. Let's get into continuity. First, we start with continuity at a point. Make sure you know these 3 conditions, because on the first exam, you'll definitely have an item that relates to this. So it's really pretty easy. Your function has to exist at that input value. The limit has to exist, and the limit has to be equal to the function value. So if we look back at our warm-up, what do you think? Would this function f be continuous at x equal to -2? Good, it would not, because the function does not exist at -2. Remember, there's an open circle on the graph, so therefore it would fail the first condition, and there's no need to go on to the other conditions. It is not continuous at x equal to -2. So let's continue on. Oh, I was ahead of myself. So using the first one, f at -2 is not defined. So f is not continuous at x equal to -2. So it fails condition 1. Now here are a few examples of discontinuity at a point. The first one is kind of like our example, right? At C, we have an open circle right here. So the first condition fails. Now the second one, if you notice at f of C, what part fails? Good. The limit as x approaches C from the left side of this function, f of x, whatever it is equal to what? Good, it's equal to this one y value, whatever that may be, right? Call this y1, right? And the limit as x approaches C from the right of f of x is equal to, good, this other y value, call it y2, and y1 is not equal to y2, so the limit does not exist when you take the superscript off. And I'll put D and E for does not exist. Good so far? So it fails condition 2. Fails condition 2. Now over here, so this one will say fails condition 1. This guy fails condition 2. Now, what about this one? Good. F at C exists. Do you see that f of C has an output of, call it y1? So we could say that f at C is equal to y1, and that would be our first condition, so that works out, right? Second condition, the limit as x approaches C of our function, f of x, is equal to this y value, call it y2. And so that one works out. But the third condition, right, do you see that f of C is not equal to the limit as x approaches C of our function? So it fails condition 3. So any one of those conditions, failing any one of those conditions makes existence blah. If you fail one of the conditions, then the function is not continuous at the input value of interest. All righty? Here we go. Now if we examine continuity on an open interval, you basically have to have continuity on every single of the infinitely many points within the interval. So often what we look at is we look at the problem children, like if you have a rational function, where would the denominator be 0? If you have a radical function with an even index, like a square root or a fourth root, what values of x would make the radicand negative? We look for things that won't work so that we can figure out what does work. So again, if we look at these different types of discontinuities, we've already established that in each of these cases, the function that's given is not continuous at x equal to c. If it's a single order pair, like in the first example, this would be considered to be removable, a removable discontinuity. But if there is a vertical asymptote, or if there's a break, like a jump, there's no way we can just simply replace a single point to make that a smooth curve, right? So here in example A and C, we have removable discontinuities. This is considered removable because, again, it's just at a single order pair where there's an issue. And over here, it's non-removable, or when there's a vertical asymptote, it would be non-removable. Let's look at our first example. We want to draw the graph of the following functions with the given characteristics on the open interval from A to B. So part A asks us to draw something where the function has a removable discontinuity when x is 0. Why don't you give that a try and see how you do? Okay, let's see how you did. So if this is x, and let's say that this is f at x, and we want something that has a removable discontinuity at x equal to 0, we could have something along the lines of, I don't know, let's do something. Let's say that we've got something piecewise. So it has an output of an ordered pair here, an open circle right at x is 0. Do you see that that one would be considered removable? Because we just have to deal with these two ordered pairs going on right here. Good so far? Awesome. Now down here, we want something which is non-removable. So if we draw something with a vertical asymptote at x equal to 0, you can see here that that would be a vertical asymptote. So that would be a non-removable discontinuity. All righty. The existence of a limit. So the good news here is that we've already talked about a lot of this section because we have already examined one-sided limits. So this should really click for you now since we've been working with them so much in the lectures. Basically, in order for a finite limit to exist, as you approach your value c from the left side or the right side, you should get the same y value, the same output, the same limit. So the top graph we are examining as x is approaching c from the right side. So again, if you kind of look at this graph, trace along the graph as you're approaching c from the right side. So this is just any given x value as you're coming over here. And your limit L your limit L is this value, this y value here. Now from the left side, do you see that you get the same output value, y value? It's the same limit L. So therefore, the limit as x approaches c from the left and as x approaches c from the right is the same. And therefore, we don't have to put a superscript up there. We can just say the limit as x approaches c of f of x is equal to L. Okay, now on a closed interval, what we look at is as we're approaching, so let me put kind of a so if we look up over on the right side, what's happening if we examine this one-sided limit? What is happening as to the function, but I can't talk today. What is happening as x approaches a from the right side of this function f of x? What is it equaling to? Good. It's equal to f at a, isn't it? It's equal to f at a. So as we are going this way, do you see that our one-sided limit from the right side of a is approaching f of a? And what about as we go from the left side of b? What's happening? We're approaching. Good. The limit as x approaches b from the left side of f of x is equal to f of b. So now let's take a look here. Oops. Let's take a look here at the official definition for continuity on a closed interval. So you have to have continuity on every single ordered pair or every single input value on that interval, every single point on that interval, but you also have to have those two things we discussed. The limit as x approaches a from the right side has to be equal to f at a, and the limit as x approaches b from the left side of the function has to equal f at b. So now let's take a look at the graph of these functions and use the definition of continuity to discuss the continuity of these functions. So the first one is tangent at x, which is periodic. So why don't we just do from negative pi to pi. And this will be x, and this will be g at x. So if you recall, the tangent function is equal to the sine function over the cosine function. And the zeros of the cosine function on the one round of the unit circle are going to occur where? Good, at pi over 2 and 3 pi over 2, which is coterminal with, good, negative pi over 2. So our graph will have an ordered pair at 0, 0, pi over 4. Let's see, what are we going to do for our one? We'll have 1, 2, negative 1, negative 2. So at pi over 4, we have an output at 1. At negative pi over 4, we have an output at negative 1. So our graph will look something along these lines. something like that. So when we talk about the continuity, where would you say the problem children are? Good. I mean, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. So what we need to do is we need to discuss the continuity. So we're going to build a set. And let's just go ahead and write this in words. So x is continuous on actually, let's say over the real numbers except when x is equal to, we know pi over 2 is a problem, right? And then if we say plus k pi, let's see if that'll work. We want to get to every multiple of pi over 2 for the integers. So we want to get pi over 2, 3 pi over 2. So basically everything that's coterminal with pi over 2 and 3 pi over 2. So if I add pi to pi over 2, I get 3 pi over 2. If I add 2 pi, I get something coterminal. So this works out, and I have to identify k is an integer. So to write that in a set, you build a set. So you describe the value of interest. So this is x, such that, and we describe x. X belongs to the real numbers, and x cannot equal to pi over 2 plus k pi, where k belongs to the integers. All right? Good so far? So we've described the continuity for x so we've described the continuity of x in a set. Okay, let's try this guy next. Go ahead and pause the movie and see how you do. Okay, let's see how you did. So let's graph these in a few different colors. This will be our x and this will be our y. And I guess we'll just go to plus or minus 10. So if we graph this one in blue, and this guy in green, and this guy in black, we'll have our picture. So the first one is an absolute value graph for x less than or equal to 2. So the trick on these piecewise functions is to graph each piece, including these border values. And when it's non-inclusive, like in the middle interval, you just put open circles where the output would be. So for the first one, we have an absolute value graph for x less than or equal to 2. So we'll have an ordered pair at 2, 2. And then the graph will go like a V. And that's how our graph behaves for x less than or equal to 2. Now the middle graph is non-inclusive, so it behaves as negative x for x between 2 and 4. So we'll have an open circle at 2, negative 2. And we'll have an open circle at 4, -4. And then it'll be a line in between those. Good so far? Great. And then the next one's a parabola, x squared over 4 for x greater than or equal to 4. So right at 4, we'll get an output of 4. And then that's included. And then we can do, I don't know, let's do 6. If we do 6, 36 divided by 4 is 9. So 6, 9. So it'll be increasing real, it'll be increasing kind of along like those lines. Good so far? Awesome. Alrighty, so this is our picture. So now we need to discuss the continuity. Well, there's no issues. Why don't you guys go ahead and stop me when you think there's an issue, okay? I'm going to start at the leftmost part of the graph and just cruise along. So get ready to stop me. Ah, good. You stopped me. All right. So here we go. This one you've identified as a problem child area. And where else? Good. Over here when x is 4, that's also a problem area. Now, if you take a look using the 3 definitions of continuity at a point, right? So at x equal to +2, the first one says that our function has to exist. So f at 2 equals what? Good, 2. So that one worked out, didn't it? Now the second condition is that the limit has to exist. So the limit as x approaches 2 from the left of our function y is equal to what? Good, 2. The limit as x approaches 2 from the right side of y is going to be good, -2. Do you see that? So the limit as x approaches 2 without any of the superscript does not exist, so it fails. So it fails here. I don't want to put an X. And do you see at x equal to 4, we have the same problem? The function exists. So f at 4 is equal to, what was it? Good, 4. But it fails this one because the limit does not exist. Only the one-sided limits exist. Okay? So we would say, discussing the continuity, we would say that y is continuous on -infinity to, good, to 2 non-inclusive union, 2 to 4 non-inclusive union, 4 to infinity, and we're good to go. All right? How'd you do? Awesome. So there's some properties of continuity. So this is pretty cool. If you have a continuous function and you multiply it by a scalar, you still have a continuous function. So the sum or difference of 2 continuous functions is also continuous. The product of 2 continuous functions is continuous, and as is the quotient, as long as you don't get an output of 0 in the denominator for a quotient. Now, there's some special types of functions that are continuous at every point in their domains. Polynomial functions, rational functions, radical functions, and trig functions. But remember that caveat, they're continuous at every point in their domain. So wherever there would have been a domain restriction, you're still going to have that going on. And then again, continuity of a composite function. If you've got, G continuous at C and F is continuous at G at C, then the composition is continuous at C. So let's take a look at the intermediate value theorem. This theorem says that if F is continuous on the closed interval from A to B and K is any number between F of A and F of B, so K is A, good, a Y value, then there has to be at least one number, C, that's in the domain in between A and B inclusive, such that F at C has an output of K. Right? So you may have seen this before in the zero existence theorem. Sometimes they put that in pre-calc books. If you have a continuous function and at one side of the closed interval you have a positive and at the other side of a closed interval you have a negative output, then there has to be a real zero in between. So that's kind of a special case of this intermediate value theorem. So let's check this out. We're going to consider f at x equal to cosine at 2x on the closed interval from 0 to pi over 2. So here we go. Let's have this be 1, -1. You can do pi over 4 and pi over 2. So let's see what we get. So if we're sketching the graph of f by hand, remember that it's going to complete more quickly since we're doubling x. So cosine at 0 is 0, right? 2 times 0 is 0. Whoops, I'm making up my own math. Thank you for catching me. Cosine at 0 is 1. And then if I double pi over 4, do you see I'd get pi over 2, and cosine at pi over 2 zeroes out. And then if I double pi over 2, I get pi, and cosine at pi is -1. So we'll get a graph that looks something like this. Of course, this is x and f at x. Good so far? Awesome. All right, so now state the reason why we can apply the intermediate value theorem. What was the condition? Good. F is continuous on the closed interval from 0 to pi over 2. That was the condition for using the mean value theorem. Alrighty, use the intermediate value theorem to find C such that f at C is a half. So the K in this case that from the theorem is a half. So how can we find that value? Well, we can take f at C equal to 1/2, right? And what would f at C be? What was our function? Cosine at 2x, right? So f at C is just cosine at 2c would be 1/2. So at what values on the interval in question from 0 to 2 pi does the cosine function have an output of 1/2? Good, it has an output of 1/2 at pi over 3. And then if we had doubled that interval, we'd go to pi, but the cosine function is negative in the second quadrant, so we're good to go. So now if we multiply that by 1/2, C is going to be pi over 6. And that's your answer. And if you look at the graph here, at pi over 6, which is about, it's a third of pi over 2, right? So it'd be about here. We're up at 1/2. So right here we've got this ordered pair of pi over 6, comma, 1/2. So this ended up, the pi over 6 ended up being our C, And the 1/2 ended up being our k from the intermediate value theorem. All right. We use direct sub right here. We'll get 2 over 2 plus 2, right? Which is just equal to 1/2. So that one didn't give us any trouble, right? Now, what about this guy? When we use direct sub, we get root 4 minus 2 over 4 minus 4, which is 0 over 0. And what did that mean? That meant, good, more work. Let's rationalize the numerator. So we have the limit as x approaches 4 from the left of root x minus 2 over x minus 4. If we multiply by root x plus 2 over root x plus 2, we will get the limit as x approaches 4 from the left of, great, x minus 4 over x minus 4 times root x plus 2, which is, good, these divide out. So we'll have the limit as x approaches 4 from the left of 1 over root x plus 2. And then now, using direct subs again, we'll get 1 over root 4 plus 2, which is, good, 1/4. So you see that it doesn't really matter if you have a one-sided limit. If you get something that's indeterminate, you still work with it to get it in a format where you can determine the limit. Let's take a look at this guy. Let's make a picture of this one. We'll probably want a picture of both of these, so a little smaller. And then we'll do another one over here. Oops, doesn't want to move it. All right, finally. So let's check it out. We've got this guy over here. I don't know. Let's this one you see is going to be pretty close. It's going to either be 1 or -1 most of the time. So let's just make this be 1 and -1, and then we want to go further here, so let's go to 20, and this would be -20. And if you take a look, let's just go ahead and plug in 20. So when x is 20, you would get 20 minus 10 in the numerator. In an absolute value would be absolute 10, and absolute 10 is 10. And you'd get 20 minus 10, which is 10 in the denominator. So you'd get a +1. So you'll get an ordered pair at 21. And do you see that it's going to behave that way until you get to x equal to 10 exactly? Because why? You've got an excluded domain value. Do you see that when x is equal to 10? So you'll have an open circle here. But what if we had 19? 19 minus 10 is 9. Absolute value of 9 is 9. And you'd still get 1, right? So you'd basically get a horizontal line right up at 1 until you got to 0. And then do you see it'll turn negative over here because the denominator would end up being negative? So this is going to behave, this graph is going to behave like this. So what would you say about the limit as x approaches 10 from the right? Will it exist? You bet it will exist because it's just a one-sided limit. Do you see a one-sided limit? And that one-sided limit from the right side is perfect, +1. Would the two-sided limit exist? No, because you'd be approaching different values from either side, so that one wouldn't exist. As you approach, x approaches 10 from the left side, you get an output of -1, and so the limit wouldn't exist unless you had that superscript on there. Only the one-sided limits exist. Okay, so the next step, we've got this graph, and if you recall, it's going to look something along these lines, isn't it? You'll have, in the first quadrant, you'll have values, and so when x is positive, all the outputs will be positive, right? And when x is negative, all the outputs will be negative, right? So you're going to have outputs just in the first and the third quadrants. So what would you say as x approaches 0 from the left side? If you look at this graphically, do you see you're going down to -infinity? Good. So basically, this one, why don't we say equals -infinity? Technically, it does not exist, but that gives us useful information about how the graph is behaving as we approach the vertical asymptote. Okay? So this is the official answer, but it's useful information to know if it goes to plus or minus infinity. All right, so the next section will be infinite limits, where we'll explore that idea more, and have a fabulous day. Bye.